This is the last module on the preliminaries that we need to understand the measure theory better. In this module, we'll be talking about the sequence of functions, pointwise convergence, uniform convergence, and absolute convergence. We'll achieve this by a root test, and considering different sequences of functions, we'll say that whether that sequence of function is convergent or not. Then we'll be discussing the geometric series and power series as a special case, and we'll try to find the radius of convergence for those cases. Then the two very important theorems, one is differentiation term by term and integration term by term, will be discussed, and we'll give examples how these two terms, that is term by term integration and term by term differentiation, will be used. After defining a sequence of real numbers, here we will be defining a sequence of functions. So we define a sequence of functions f1, f2, f3 and so on, as fn is a list of functions such that each of this element fn maps a given subset D of real line into real line. And once we define the sequence of function, the next job is to define pointwise convergence. Let D be a subset of R, this is a real line, and let fn be a sequence of functions defined on this D. We say fn converges pointwise on D if limit n tends to infinity fnx exists for each point x belonging to the subset of R, that is D. Now limit n tends to infinity fnx is a real number and that only depend on x. The function fx, which is the limit n tends to infinity fnx, is called pointwise limit of the sequence fn. So the limit of the sequence fn will be denoted by fx. Now we consider a few examples to understand the pointwise convergence. Fnx is x by n, x over n, this is the function we are considering. Note that as n tends to infinity, this function converges pointwise to the 0 function on real line. If we take fnx as nx as n tends to infinity, this function will increase and this doesn't converge pointwise on R, because limit n tends to infinity fnx will be infinity for any x greater than 0. Now take the third example, nx plus x square over n square, and all x belongs to the real line. Now if you take limit over this fnx over n, limit n tends to infinity fnx, I can break this into two parts, nx over n square plus x square by n square. So limit n tends to infinity nx by n square plus limit n tends to infinity x square by n square. If I take x out of the limit, we will be left with limit n tends to infinity 1 over n, and for the second term I take x square out of the limit and it will be left with limit n tends to infinity 1 over n square, and both this limit goes to 0. So that means this function converges pointwise to the 0 function. The last example that I will be considering in this slide is fnx is sine nx plus 3 by square root of n plus x for all x belonging to R. Now we can see that sine nx plus 3 over square root of n plus 1 is greater than minus 1 by square root of n plus 1, where it is less than equals to 1 over square root of n plus 1 using the property of a sine function. So now we will be using sandwich theorem. If we take the limit, the left hand limit, the minus 1 by square root of n plus 1 will tend to 0. For the right side, the same thing will happen. Limit n tends to infinity 1 over square root of n plus 1 will also goes to 0. So using sandwich theorem, the limit of this fnx will go to 0. So using sandwich theorem we can say that the function converges pointwise to the 0 function on this R. Now we will define the pointwise convergence in a more formal way. Let D be a subset of R, this is the real line, and let Fn be a sequence of real valued functions defined on this D. then Fn converges pointwise to f if given any x belonging to the subset D and given any epsilon greater than 0, there exists a natural number capital N which is a function of x and epsilon such that mod of Fnx minus fx is less than epsilon whenever n crosses capital N. So the main difference with the sequence or the convergence of sequence of real numbers with the convergence of sequence of functions is that here we have the important role of x, whereas in the sequence of real numbers the convergence depends only on the value of epsilon. Here also we can have similar sort of situation, and that is called uniform convergence. So let D be a subset of R, so we are keeping the everything same, and let Fn be a sequence of real valued functions defined on D. Then Fn converges pointwise to f if any given x belonging to B and given any epsilon greater than 0, there exists a natural number n which is a function of epsilon only, such that mod of Fnx minus fx is less than epsilon whenever n crosses capital N and for every x belongs to D. In the above definition, the natural number capital N depends only on epsilon. Therefore, uniform convergence implies pointwise convergence because it is true for any x, whereas the converse is not true. So this is the formal definition of uniform convergence. Now we'll consider a few examples. Consider Fnx as nx over 1 plus n square x square. This function converges pointwise to 0. In fact, we can see that 1 plus n square x square is approximately equals to n square x square as n gets larger. Because if n gets larger, there is hardly any difference between 1 plus n square x square and n square x square. So we can write limit n tends to infinity Fnx as 1 over x limit 1 over n, and we know limit 1 over n tends to 0. But for any epsilon less than half, Fn over 1 by n minus f of 1 by n, it can be seen that it's nothing but half minus 0, that is greater than epsilon. Hence, Fn is not uniformly convergent. Though it is convergent, it is not uniformly convergent. If it is uniformly convergent, then we know a function is obviously pointwise convergent. So this is one example where it can be shown that pointwise convergence doesn't imply uniformly convergence. Now we'll have a theorem. Let D be a subset of R and let Fn be a sequence of a continuous function on D which converges uniformly to f on D, then f is also continuous on D. Once again, we are omitting the proof, we'll just stating the statement. Now we'll come to one very important series called power series. Power series is always of the form 1 plus x square plus x cube, something like that. So the question will be asking, does this series converge? Well, whether or not this power series converges depend on the value of x. Common sense says that if x is very large, for example x is 100, then fx will be 1 plus 100 plus 100 square plus 100 cube and so on. So this will not converge, it will go to infinity. But if it's very small, say 0.1, then 1 plus 0.1 plus 0.11 plus 0.011. So if we add this will not go much, it will be 1.1111 and so on. So in fact, since this particular series is geometric, it will converge whenever mod x is less than 1 and diverge whenever mod x is greater than 1. And in general, a power series converges whenever it is close to 0, and it may diverge if it is far away from 0. And the maximum allowed distance from 0 is called the radius of convergence. These are the very important term, radius of convergence. Now consider the series sum over minus 1 to the power n plus 1 over n square. So if I put different values of n, it will be of something like that, 1 minus 1 4 plus 1 minus 1 by 9 minus and so on. So the question is that whether this series converges. It cannot possibly become divergent if we change some of the terms to negative. just keeping this into mind, we can say that we know sum over 1 over n square converges, and this is a term, this is a series obtained from the series 1 over n square, where we are subtracting few numbers, so this will not hamper the convergence. Now we'll define what we mean by absolute convergence rule. So if the positive series sum over n from 1 to infinity mod of an converges, then the series sum over an must converge as well. So to check the convergence of any series, it's best to find the absolute convergence. If it is absolutely convergent, then it is convergent. Be aware that absolute convergence rule only works for convergence. So whenever sum over mod an diverges, it is still possible for the series sum over n to converge. So this will be applicable only for convergent series. One famous example is the alternating harmonic series. So it will be something like that: 1 minus half plus 1/3 minus 1/4. Though the harmonic series itself diverges, the alternating harmonic series actually converges. This is a direct result of the subtractions. Each term partially cancels with the previous term, so resulting in a total sum that is finite. So this alternating harmonic series is convergent, whereas the harmonic series itself is divergent. Now we will define what do you mean by root test. We called it as absolute value theorem. Let sum over n be a series, and let r is equals to limit n tends to infinity 1n, that is the nth square root of an. Now if r is less than 1, then the series convergence. If r is greater than 1, the series is divergent, and if r is equals to 1, the root test is inconclusive. Just to apply this rule or test, we consider the sequence minus 2 to the power n over n square 3 to the power n. So if we take the definition of r, it will be 2 over 1 into 3, that is 2 by 3. Since 2 by 3 is less than 1, this series is convergent. Now we will ask the question, for what values of x this geometric series will converge? 1 plus 2x plus 4x square plus 8x cube and so on. So we can write this series as sum over n from 1 to infinity 2 to the power n into x to the power n, and by root test we can get r as 2 modulus of x. If modulus of x is less than half, then the series converges. If mod x is greater than half, then the series diverges. What will happen if x is equals to half? Then the series becomes 1 plus 1 plus 1 plus 1 and so on. So it is a divergent series. If x is equals to minus half, the series becomes 1 minus 1 plus 1 minus 1. Once again it also diverges. So this is how we apply the root test. Now we consider the general power series of the form Cn x to the power n, n from 1 to infinity. Then there exists a radius r for which the series converges for mod x less than r and the series diverges for mod x greater than r, and this r is called the radius of convergence. For the few examples, we will be trying to find the radius of convergence. So this is the series 1 over n 3 to the power n x to the power n sum over n from 1 to infinity. By root test, after doing some manipulation, r can be written as 1/3 mod x. If mod x is less than 3, then the series converges, and if mod x is greater than 3, then the series diverges. So the radius of convergence is r is equals to 3. Now if you consider the series 1 over n factorial x to the power n sum over n from 1 to infinity, so by root test we get r as 1 by infinity and mod x, and that equals to 0. So whatever be the value of x, r is equals to 0. So the radius of the convergence is infinity. By root test we can find the radius of convergence in this way. Now we will define very important result or very important term is term by term integration and differentiation. The necessity of this thing is that sometimes the calculus one needs to do involves functions which cannot be defined in a traditional way by a formula, but only in terms of a convergence series or elementary functions. For these cases, we can use this property, term by term integration and differentiation, and they will be used in measure theory quite often. So the first theorem, which corresponds to the term by term integration. Let fk is a function, its mapping ab, this is the closed interval, and it maps ab to r, is the real line, and this mapping is valid for all k. So we will have f1, f2, f3 and so on. We will be assuming that these functions, they are integrable on this closed boundary ab, and sum over k fkx converges uniformly on that closed interval ab. So this is the setup, that all the functions which maps the closed interval ab to r are integrable, and sum over fkx, the series, converges uniformly on that interval. Then the sum fx, which is sum over fkx, k runs from 1 to infinity, is also integrable, and sum of integration a to b fx dx can be expressed as sum over k integration a to b fkx dx. That means integrating the function which is the sum of all these functions is nothing but sum over integrating all the individual functions, then adding them together. So this is called term by term integration. So we will be integrating all the functions first, then we will add them to find the sum. This is called term by term integration. Similar to this, we will have term by term differentiation too. Here also we will be defining fk, which maps the closed interval ab to real line, and this is true for all k, and they has continuous derivative on this bounded on this closed interval ab. Suppose further that the series k from 1 to infinity fkx naught converges at some point x naught which belongs to the closed interval ab, and the series fk prime x, this is the first order derivative of the function fkx, converges uniformly on that closed interval ab, and fx is sum over k from 1 to infinity f prime kx. Then the series sum over k from 1 to infinity fkx converges at every x belonging to that closed interval ab, and the sum capital Fx is sum over k from 1 to infinity fkx is differentiable, and the property is that f prime x is equals to small fx for each x belonging to that closed interval ab. And secondly, convergence of k from 1 to infinity fkx, this series to capital Fx, is uniform on this closed interval ab. Now the proofs of all these two theorems are beyond the scope of this lecture, so we will be showing how these two things we are using in our algebra. So the function fx 4 over 2 minus x square is the derivative of the function 2x by 2 minus x. If you take the derivative of 2x by 2 minus x, we will be getting 4 by 2 minus x square. And 2x by 2 minus x, once again I can write it in a series as n from 1 to infinity 1 over 2 to the power n minus 1 x to the power n. This is a convergent series, and this series converges whenever mod x is less than 2. To obtain a power series representation of fx, we differentiate this series term by term, and we can find 4 over 2 minus x square is equals to, if I take the differentiation of the term, 1 over 2 to the power n minus 1, we are differentiating with respect to x, so it will be n into x to the power n minus 1, and if we take n minus 1 as n and we change the suffix, it will be n from 0 to infinity n plus 1 by 2 to the power n into n into x to the power n, and this series also converges whenever mod x is less than 2. So this is one example of term by term differentiation. Now consider the second example. Suppose we are to ask the integrate 0 to 1 1 plus 1 by 1 plus x to the power 4 dx. Well, our simple mathematics will not be able to solve this. So what we will be doing? We will be using the concept of series. And from integrating 0 to 1, we can write the function as 1 by 1 minus x to the power 4 dx. So this is nothing but the series n from 0 to infinity minus 1 to the power n x to the power 4n dx. Now integrating 0 to 1, 1 by 1 plus x to the power 4 is equivalent by first taking the sum n from 0 to infinity and integrating each of these functions 0 to 1 minus 1 to the power n x to the power 4n dx, which is relatively easier to do, and it can be seen that it will be n from 0 to infinity minus 1 to the power n by 4n plus 1. This is an alternating series which by the alternating series test converges. So we can do this using term by term integration. We have discussed point by point pointwise convergence, uniform convergence and absolute convergence of series of functions. We have also shown that if a series of functions which are uniform convergent, they are convergent too. But if they are point convergence functions, sequence of functions, they might not be uniform convergence. And this can be achieved using the results that we stated. We also gave few examples where we can show that this sort of convergence happens and how to find those. This can be achieved using different tests that we proposed or different theorems that we mentioned. Though we have intentionally skipped the proofs of important theorems that are mentioned mainly in the last slide, this can be found in any textbook related to real analysis.